In this video, we will continue with the control structures discussion. We have so far talked about if statements and switch statements, which have to do with what's often called selection. And now we're going to talk about loops. And basically, there are three categories of loops: top tested, bottom tested, and what's often called enumerated loops. Well, a top tested loop is when before we drop into the body of the loop, and in our decision of whether to drop into the body of the loop, we make a test, a Boolean expression. And if that expression is true, we're going to drop into the body of the loop, and then we'll test again. And if it's true, we'll drop into the body of the loop, and then eventually it'll be false and we'll end. A bottom tested loop, you will execute the body of the loop, and then you do a test to decide whether you're going to continue or not. And then the enumerated loop, typically the idea is that you are deciding, I want to loop X number of times, and we'll see some examples of all of these. This is all material from Chapter 5, so you can see in the samples that we got from the textbook that there are several samples from Chapter 5, and we're going to look at a few of these examples. So to illustrate the behavior of a while loop, a top-tested loop, as you can see, the very beginning of it is making a decision. We have a condition, of course, that has to be a Boolean expression of some sort. If that condition turns out to be true, then we'll execute the statements of the loop and go back up to the top and make the test again. And if it's true, we execute and go back up to the top and make the test again. At some point, it'll be false, presumably, at which point we're done with the loop and we continue to the next statement. So this is a top-tested loop. We're testing before we perform the statements of the loop body. And so that means that given the fact that it is possible when we first drop into the loop from above, it is possible at the very beginning for it to be false. So it's possible that we will never execute the statements of the body. You will notice that the syntax is very similar to the syntax of an if statement, except that instead of the word if, we have the word while, and the while means we keep doing it as long as it's true. One example in the textbook is this thing called sentinel value. The word sentinel is often used to mean like a guard, a gatekeeper sort of thing. So you can imagine that the sentinel value is going to be this data variable. This is what's making the decision about whether we want to continue going into the loop or not. It's a term that's often used. I don't know how important it is for you to memorize that term, but it's a term that's often used when it comes to loops, and especially top-tested loops. Sometimes we're testing against the value of a particular variable, and oftentimes they call that its sentinel value. So here's the loop, as you can see, and we are executing multiple statements within that loop, which is why we needed to have a block. Similar to an if statement, if all you wanted to do was execute one statement within the loop, then you would not need the block. All you would need would be the statement. It doesn't hurt to have the curly Q braces, but you might not need them. Notice again the indentation in order to make things readable. That makes it obvious that these statements are subordinate to the loop. They're only going to execute if the loop condition is satisfied. Another feature of this particular example is the notion that first we're prompting the user to enter a value before we enter into the loop, and then after we've done something with it, then we're asking the user to enter a value again within the loop, and this will be distinguished from bottom-tested loops, as we'll see shortly. Hopefully you can glean what's being done here. We're basically going to be adding to a sum over and over and over again until we decide that we want to quit. And how do we decide that we want to quit? If the user enters a 0, that's an indication that we want to quit. And so that's why this condition right here is testing to see, as long as the value that the user has entered, which is in this variable called data, as long as that value is not 0, we're going to continue within the loop, and we're going to always add to that sum. Maybe to clarify this word sentinel, it's called a sentinel value. So it's not necessarily the variable itself that is the sentinel. It's the number 0 that's the sentinel. This value right here that we're testing for, that's the value that if that's what the variable contains, then we're going to exit the loop. So the sentinel value is this 0 right here in this particular example. So here's the example. I'll go ahead and run it. It's asking me to enter a value. So let's say I enter 0. That means we're not going to ever be dropping into the loop to add to the sum, which we had initialized as 0 here. Let me run it again. So maybe I'll put a 2, and now we drop into the loop again because data was not equal to 0. A 1, we drop into the loop again, maybe even a -5. We drop into the loop again, and now let's put a 0. And that gave us our sum, and we exited. So this first enter an int value right here took place above the loop. But every subsequent one, because we were within the loop, going over and over and over again, within the loop, every subsequent prompt, all of these took place inside the loop. So, what does that mean? That means in this particular situation, we wound up testing 4 times. We tested once for this initial input, and then we tested 3 more times for each of these inputs right here. But we only dropped into the body of the loop 3 times, which means that we will always be testing once more than we actually drop into the body of the loop when we're doing a top tested loop. And to illustrate that, let's run it with a debugger. So I'll do the same thing. I'm going to debug it. It's got a couple of breakpoints here. Here's my first. I'll go ahead and put a 2 in. And now we've dropped into the body of the loop. In other words, this test right here, data not equal to 0, that succeeded. I'm going to continue. The user is prompted again. We're at this point right here where basically it's waiting for the user to enter a value. If the user doesn't enter a value, it's just going to sit there and wait and wait and wait and wait until the user enters a value. So I'll go ahead and enter a value. And I will continue. So now we are in the loop for the second time. And we're going to add that value to the sum. So the sum was 2 from the previous one. And now we're about to add the 1 to that. So I'll go ahead and continue with that. And now once again it's asking us. So now the sum is 3. And let me go ahead and put a -5 like I'd done before. I think that's what I did before. And I'll enter it. And we are still waiting at this breakpoint. So let's continue. And now we're in the loop for the 3rd time. And so we're going to, now it's a -5. I'll do the same thing. I'll continue. And now it's going to ask us again to enter a value. I'll go ahead and enter a value 0. Continue. Let's see if it'll stop up here. It does stop up here. So now let's see. Is data not equal to 0? That's a false. So we are testing for the 4th time, and now the test is going to fail. And so finally it comes out and says the sum is 2. So always with the top tested loop, you are testing 1 more time than you are actually executing the body of the loop. So if we've tested 9 times, then we would have looped 8 times. In general, if we test n times, we will enter the body of the loop n-1 times. So that was an example of a top tested loop. And now we see an example of a bottom tested loop. Again, it uses the word while here, but now the while is after the loop body. And before the loop body is the word do. So in this case, we're going to execute the body of the loop. And then after we execute the body of the loop, we test to see if the condition to continue is true. And if so, we continue. So in this case, we're always going to execute the body of the loop at least once, unlike a top-tested loop. With a top-tested loop, it's possible not to execute the body of the loop. And as a matter of fact, in this case, we're going to be doing the test the same number of times as we execute the body of the loop. So here's this test do while, and we can see this. And if I go ahead and run it, notice, by the way, in this case, that the prompt is at the beginning of the loop. So we're always going to at least be adding one thing to the data. As a matter of fact, even if we entered a 0, it would at least add a 0 to the data, but then it would test. The net effect is going to be the same. But keep in mind that we're adding the 0 this time. We weren't adding the 0 the other time because we were testing to see whether it was a 0 or not before we entered the loop. But here we're not testing until after. So if I was to run this, I'll do basically the same thing I did before. If I remember, it was a 2, and a 1, and a -5, and a 0, and then we wound up with that same result. And of course, you can kind of see, I don't think I'll bother using the debugger with this, but you can kind of see that we're executing the body, then we're testing. If the test succeeds, then we go back up to the top and we execute the body again, and then we test, and we keep doing that until the test fails. So this is an example of a bottom tested loop. The do while in Java is a bottom tested loop. And so that's what we saw here. The test is at the bottom. Now let's talk about for loops. For loops, the syntax looks a little bit confusing, but hopefully you're going to be able to make sense of it with some practice. So there's the word for, and then within the parentheses here, we actually have 3 separate things happening. The first thing that's happening is we are initializing what's often called the control variable, sometimes called the loop counter variable. And this is actually an assignment statement. We're assigning a value into that. And that assignment statement is only going to happen the very first time we drop into the loop from above. And then for every time that we go back up to the top of the loop, there's a test. And what is that test? It's a Boolean expression. And generally speaking, what that Boolean expression is doing is going to test to see something about the control variable. Usually, if we wanted to loop 10 times, for example, we'd test to see if that control variable was less than 10. So that's going to take place. Once that takes place, and if this test succeeds, then we enter into the body of the loop and we execute whatever statements there are in the body of the loop. Then we go back up to the top of the loop again. Now this time, since we're going back up to the top of the loop again, we're not initializing this, because we only do that when we drop in from the beginning, but instead, what we're going to do is we're going to do some adjustment, and this adjustment is typically another kind of an assignment statement. And we're going to do some adjustment. Typically, the adjustment is for this control variable, and then we're going to test again. So let's see again what the order of events is taking place here. The very first time we drop into the loop for above, we initialize, we test. If the test succeeds, we execute the loop body. Then we do our adjustment, and we test again. If the test succeeds, we execute the loop body. Then we do our adjustment again, and then we test again. And, after doing this some number of times, this test will fail, and then at that point, we end the loop. So really, in a sense, this is another example of a top-tested loop. It is possible depending on how you initialize your control variable, that we would never enter the body of the loop. But in practical point of view, usually the intent is that we are going to be looping at least one time, but it is possible to have a situation with a for loop where we never enter the body of the loop, just like in other top-tested loops. So here's the flowchart for that. Here is our control variable expression. This is the thing where we're initializing the control variable. Here's our test. Our test succeeds, we execute the body of the loop. Then we do that adjustment. That's that third piece of what's inside the parentheses. And then we test again. And if the test succeeds, we execute. And then we adjust again. And then we test again. And we execute. And we adjust and test. And at some point in time, the test fails. And at that point, we're done with the loop. So here was an example where we used a variable. We've declared the variable. We called it I. By the way, there's very simple little variable names like I and J are very, very common for loop control variables. Typically, the loop control variable, the only purpose for having that variable is for controlling the loop. So here is our initialization. Here is our test. And then here is our adjustment. And what are we doing? We're adding 1 to the variable I each time. So in this scenario, we're going to wind up looping 100 times because it starts at 0, then it's 1, then it's 2, then it's 3, then it's 4, then it's 5, then it's 6. And every time that test is going to succeed, this I less than 100 is going to succeed until I becomes 100. And so at that point, it would fail. So in this case, we would have done 101 tests because the first time I would have been 0. And the last time I would be 100 because every time we're adding 1 to it. And so finally on that 101st time of the testing, then the test is going to fail. So again, top tested loop. Test takes place once more than the actual execution of the body of the loop. This syntax is slightly different from the syntax above. Notice in this right here, we actually declared that variable called I above the loop. And what that really means is that that variable I can be used subsequently if you wanted to after the loop. But in this case, which is probably the more common case, because as I said, usually the purpose of this loop control variable is solely for controlling the loop. So in this case, we're actually declaring I at the same time as we're doing the assignment here. Now what that means is that this variable called I only exists as long as the loop is executing. Only exists within these few statements right here. In other words, we can access I from within the loop. As you can see, here I am actually accessing the variable I. But if I tried to access I, if I tried to put an assignment or print out what the value of I is afterwards, I'd get a syntax error because that statement would be outside of the scope of this variable. Later when we get to talking about methods, we're going to get a better idea of this notion of variable scope, which ties in directly with the notion of the duration of a variable. But this is what I can say about this particular variable called I here. Its scope is only within the body, not within the body of the loop, but it also has a scope in the conditions of the loop here. So its scope is limited to statements between the word for and the end of this curly Q brace. And also its duration, it's going to last only as long as this loop is continuing to execute. Scope and duration are things that are going to be important for you to learn, and we're going to be talking more about that when we get into talking about methods later on in the semester. I am quite sure that you're going to be doing a lot of nested looping in this class, And not just nested looping, but also nesting of various structures. You can have loops inside of loops. You can have different kinds of loops or the same kind of loop inside another loop. You can have if statements inside of loops. You can have loops inside of if statements. There's all kinds of nesting that you can be doing. And here's an example of using a nested for loop. And we'll see that the nested for loop comes in very handy for doing kind of grid sort of things. A non-nested loop, like we had before, could be something that would give us a list of things. As a matter of fact, here we would have a list of sentences. Hi, I equals 0. Hi, I equals 1. Hi, I equals 2, etc. But now we'll see that we can be doing stuff having to do with more of a grid or a table or a two-dimensional kind of structure if you're nesting one deep. And if you are nesting two deep, you could have three-dimensional structures. And if you are nesting four deep, you could have four-dimensional structures being taken care of for this. So here we have a situation where we have one loop, one variable called I, and that's our outer loop variable. And for our inner loop variable, we have another variable called J. And each time, and we're doing a test here, I less than outer loop limit, whatever our outer loop limit happens to be. And we have another test, J equal inner loop limit. So we can have two different limits. So maybe outer loop limit is 5 and inner loop limit is 10, for example. If we had a situation where outer loop limit was 5 and inner loop limit was 10, then what that would mean is that we would be going through this outer loop 5 times. And each time in that outer loop, we would be going through this inner loop 10 times. So how many total times are we going to go through this inner loop? Well, the answer to that is 50. 5 times 10. Because each time we're just incrementing by 1 here. In both cases, the inner loop counter and the outer loop counter is incrementing by 1. So when I is going to be 0 that first time, we'll have I being 0, and then J being 0, and then J being 1, and then J being 2, and then J being 3, all the while I remains at 0, until we get to J of 9, which is still going to work, and then assuming that inner loop limit was 10, once we get to J of 10, that's going to fail, and then finally we'll be done with this inner loop. We will have, if there were other statements within the outer loop that we're executing, we would execute those, go back up to the top. I will be 1 at this point, and then once again, J is going to start at 0, then 1, then 2, then 3, etc. So notice what that means. That means J is going to be reinitialized to 0 each time we drop into this inner loop from above. So every time we drop into a for loop from above, this initialization is going to take place. And then as that loop continues, we're doing a test, we're executing, and we're doing the adjustment. You can see how complex the flowchart starts to get. Here we have whatever statements that preceded the loop, the outer loop. We're initializing the outer loop counter. We do a test. Assuming that it succeeds, we execute whatever statements preceded the inner loop, and we initialize the inner loop counter. We do our test, and as long as that test succeeds, we continue to execute the statements and increment and test and execute and increment and test until that ends. Whatever remaining statements were in the outer loop get executed, and then we're incrementing, that's our adjustment, and then we test again, this outer loop, this would be our I variable in the previous example, and then the whole thing starts again. So now if we're in the second time in this outer loop, and we are dropping into this inner loop from above, again we're doing our initialization. We would have initialized that J variable to 0 again. And just to get to the syntax again, notice again, this int I equals 0, this I is only going to last as long as all this stuff is happening. And this J is only going to last as long as this stuff happens. And then J is going to disappear, and we get back up to the top here, and I still exists. We would have increased it to 1. But now we're dropping in here, and that J that had disappeared, there's a whole brand new J now, and it's going to last as long as this particular loop is executing. And then J will disappear again. And then after all is said and done, and we're completely done with this outer loop, I will disappear as well. So the textbook has a nice little example here called the multiplication table, and this will illustrate what I was talking about when I said a nested loop can give us something that looks like a grid. So here in chapter 5, we have multiplication table, and I'm just going to go ahead and run it, and let's see what it gives us. And look what it gave us. It gave us a grid. It gave us the multiplication table. 1 times 1 is 1. 1 times 2 is 2. 1 times 3 is 3. 5 times 3 is 15. So this is a grid. Now there's a lot of things happening in this code. Maybe to illustrate again, before we have the multiplication table itself, we have some headers coming out, we have some lines, some dashed lines coming out, and then even for each line of the grid, we are prefacing it with the row number, if you will. So let's see how the code is doing that. So as you can see, first we just had the simple print line printing out the words multiplication table. And that gave us a line. And then we printed a few spaces. And then we have this loop. This is not a nested loop, by the way. This is just a loop. Here's our nested loop down here. 4, and then inside it another 4. So this is not a nested loop. It's just a loop. And that's what's giving us the headings. 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice we're not using the word print line here. We're just using the word print. And also here, recall that there was a print line, system.out.print line, and there's also a print. These are part of the output stream classes. So print means it doesn't go to the next line. It just prints whatever it does, and then the cursor is sitting there waiting for the next print to take place. So all of this stuff happening right here, starting at 1 and going up to 9, including 9. Notice the less than or equal to here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then finally, J would have been 10, and the test would have failed. So it actually did execute 9 times, and so we have 1, 2, 3, 4, 5, 6, 7, 8, 9 happening. And then we do a print line, and we're putting this \n. You should know what that is. That is the end of line character. So that's taking us down to the next line, followed by all of these dashes. So that's why we have these dashes for the multiplication table. And then finally, the nested loop here. So we're looping again 9 times. We have an outer loop variable called I. And we're looping 9 times each time in the loop. We have an inner loop that's taking place, but let's not worry about the inner loop right just yet. Let's take a look and see what this system.out.print is doing. I concatenated with this bar right here, this vertical bar right here. So here's when I was 1, and then here's when I was 2, here's when I was 3, 4, 5, etc. So these things right here are coming out as a result of this print statement. And then once this print statement has executed, and basically we're at this bar right here, and it wasn't a print line, so we didn't go to the next line, and that's when we are doing, within the loop, we are doing another statement, and this is an interesting statement, printf. And what this printf is print with format. This method right here, printf, is a formatted print. And we're specifying the formatting here. This %4d means that each print that comes out is going to wind up being 4 spaces long, or at least 4 digits of length. which is why we're ensuring that these values are coming out lined up with each other. I'll show you what happens if we don't do that. And what are we doing? I times j. So the loop counter variable of the outer loop and the loop counter variable of the inner loop are being multiplied together to give us the values that we see in here. And then, of course, printf is not a print line either. So we get all the way, when I was, for example, 1, when j was 1, 1 times 1. When j was 2, 1 times 2. When j was 3, 1 times 3. Finally, j was 9, 1 times 9. At that point, j becomes 10. This test right here failed, so we're done with the inner loop. And this print line just took us to the next line, so that the next time we came to the top of the outer loop, and now I becomes 2, that's when this comes out. And then once again, we're initializing j to 1. Remember, every time we drop into the body of a loop, we are doing this initialization. So this is the second time we are dropping into this for loop. And so j once again becomes initialized to 1. And so now it's going to be 2 times 1, 2 times 2, 2 times 3, 2 times 4, etc. So hopefully you get a little bit of an idea of what the behavior was with this. I'll run it with the debugger shortly. And this was the notion of the printf. We're specifying that it's going to be an integer with a width of 4 spaces. So otherwise, look at this, 1 or 2 digit numbers would take the same space in the output. Well, let's take a look and see how that would have taken place. So let's play with this a little bit. So first, let's illustrate what would happen if this was just a print instead of a printf. I'm going to go ahead and get rid of the printf. I'm going to get rid of the formatting, and let's see what we're going to wind up with here. And you can see that doesn't work out too well. Well, maybe you say, well, let's just put a space between them, and that might work. So let me just do, I'll do a print and maybe make it a, can't make a space with this and see what happens. You'd think, okay, maybe that'll solve the problem. But it doesn't. And as you can see, because sometimes you have 1 digit and sometimes you have a 2 digit, so basically, if we really were going to be doing this just using a print, we'd have to make a distinction between 1 digit and 2 digit numbers. And that, yeah, we can do that, but that's maybe a little more work than it's worth, which is why we do this instead. And we make this a printf. And that's why the values are going to come out looking good, formatting wise. And now to illustrate this, maybe with the debugger, and to see the behavior of the for loop, I'm going to put a breakpoint right here, right before we do the loop. I'll put a breakpoint inside the loop, right before we get to the nested loop, I should say, because here's another loop right here. That's not a nested loop. I'm going to put a breakpoint right within the outer loop, and maybe also within the outer loop after the inner loop has completed. And then I'll also put a breakpoint within the inner loop as well. And let's take a look and see what happens when we run this in debug mode. So now we get to the point where the word multiplication table came out and these values came out. That was a result of all of this stuff happening. Let's take a look at what variables we have. Well, we have args. We don't have j. J was here. There was a j for a minute. As a matter of fact, let me show that. I'm going to stop this. I'll put a breakpoint here. Now we're putting a breakpoint within this loop right here. And here we are, and there is in fact a j. You can see the j, and you can see the j increasing. Boom. 3, 4, 5, 6, 7, 8, 9, And then we're going to go back up to the top of the loop, and it's going to fail this time. Watch what happens to J. Disappeared. So again, we're illustrating this notion of the duration of a variable. That variable only lasted as long as the for loop was running. So now we're here, about to print out this line. If we wanted to look at what we've got at this point, we've got multiplication table. We have this line being printed out. And you'll also notice, by the way, if I look at the variables, there's no such thing as I yet. If I was to hover over I here, I would say I is not a known variable in the current context because we're not yet there. And so let me go ahead and run this. So now we're the first time in the loop, and there's I. I started off at 1. That's because we initialized at 1. We look at our output. We've got the little line here. Notice how, as a result of this print line right here, we had gone to the next line. We had printed out all these dashes, and because it was a print line, now the cursor is at the line underneath it. The distinction between a print line and a print. So here we are. We're about to print this first bar out. Let me go ahead and continue. And there's our first one with the bar. And lo and behold, we should see that there is now a variable called J, and J is 1. I is 1 and J is 1. And now in our second time in the inner loop, J is 2. And then J is 3. And then J is 4. I is still 1 each time. Seven, 8, 9. So now J was 9, and this test had succeeded. Now we're about to print the last one out. By the way, notice what the output looks like here. So we're at 8. Haven't yet gotten to 9 yet. Going to get to 9 here. And we printed 9 out. What happened to J? It doesn't exist anymore. And now we're at the end of the line, but we want to go to the next line, which is why we did this print line here. We go to the next line, and there you can see the cursor's now at the next line. And so now we are the second time in the outer loop. I is 2 now. We don't have a J yet. But now we do because we're in the inner loop. So now 2 times 1. 2 times 2. 2 times 3, etc. And you can see the output gradually increasing. So hopefully that gave you a little bit of an idea of the behavior of nested looping. And after taking the breakpoints out, and I continue, and we finally get the end result. And there are a few more things I'd like to cover having to do with loops, some more examples from Chapter 5. One of them has to do with the use of the break keyword, which is a way that you can terminate your loop from inside the body, not just necessarily from the condition of the while or the for. You can, for either a while loop or a do while loop or a for loop, you can break based on some condition that takes place inside the loop. Or, alternatively, you can decide, yeah, I want to keep on looping, but I don't want to do any more statements in this iteration of the loop. Instead, I'm going to do what's called a continue, which will just take me right back up to the top of the loop, and we'll look at both of those examples. One example is 5.12, and the other example is 5.13. So you will notice in the flowchart here that you've got your loop, and I guess in this case we had a bottom tested loop, but we could also be doing this with a top tested loop. And you can see that it's a bottom tested loop, obviously, because the decision is at the bottom here. But the same principle would apply with the top tested loop. So you have some statements taking place, and maybe you reach a break. And typically that break, you're not going to always break. It would be ridiculous to always break it, but you would break based on some condition. If that condition were true, we're going to completely quit the loop. So that's what the break allows us to do. Now I'm going to run this program, and I'm going to show you the difference when we do the break and when we don't do the break with our loop. And I want you to think about this. How many times do you think this loop body is executed? And also, what's going to be the value of sum? So here's the code, and we're basically summing numbers. And basically what's happening is we have this sum variable, and every time we are adding a number to it. And what is that number? Well, that number starts off at 0, but each time of the loop we're incrementing it, right? So first it's 0, then it's 1, then it's 2, then it's 3, then it's 4, etc. And you keep adding to sum. And you would presumably be doing this 20 times. However, notice here we have this if statement that says if the sum is greater than 100, we're going to break. So that's why I asked the question, how many times do you think we are going to loop? Well, let's take a look and see what happens. I'm going to run this. And our number came out to only wind up being 14. We didn't get up to 20, even though we're supposedly incrementing each time. And our total sum came out to 105. What would happen if I didn't have this if statement here? Let me just comment it out. And I'm going to run it again. Well, if we didn't have that if statement, we would have gone 20 times, and our sum would have been 210. And now running it again with the if statement in there. As soon as the sum reaches 100, we're breaking. So how many times did the loop execute? 14 times. And what did the sum wind up being? 105. So that was the break keyword. The other keyword is the continue keyword. This would be a situation where we don't want to break out of the loop, but we want to skip statements under a certain condition. So let's check that out with this listing. And then we'll ask the question again, how many times is the loop going to execute? And then how many times is a particular statement going to execute? And here's the code. Another while loop. Again, we're starting with the sum of 0, number of 0. Each time we're incrementing number. But now we have a test to say, if it's either a 10 or 11, we're going to skip this one. So if number was 10 and number was 11, then we're going to continue, which means not breaking out of the loop, but basically going right back up to the top of the loop, which means basically skipping this statement. And let's see what happens. And it gave me the sum of 189. Actually, you know what I think I'd like to do? I'd like to also code in what the number is as well. So let's the sum is that, and the number is a number. And let's see what the number winds up being. And that'll tell us if we indeed went 20 times. And we indeed went 20 times, as you can see. What would have happened if I would have not had this statement in here? Well, our sum would have been 210. That means the 10 and the 11, which adds up to 21, we didn't include that in the sum. 210 versus 189. What do you know about that? The last one I'd like to show you is a program that's pretty involved here. As you can see, it has more lines of code than we've been looking at before. And this is called PrimeNumber. This class is called PrimeNumber, and it will show you the first 50 prime numbers. And let's actually run it, and then we'll talk about how it worked. And you know what a prime number is. A prime number is an integer that can be divided only by itself and 1. There's nothing else that will divide into the number 7, for example, but 7 and 1. And so how are these prime numbers calculated, and how did we get 50 of them out, and how did we figure out whether a number is a prime number or not to begin with? All of that stuff we're going to see because of this code. So there's a lot of stuff going on here, and let's break it out a little bit. First of all, notice we have a lot of nesting of one control structure inside another. So we have an outer loop, and that outer loop is looping as long as count is less than number of primes, which, as we can see up here, is 50. So basically it's going 50 times because count started at 0. And then within that outer loop, we have a for loop. And within that for loop, there's an if statement. So we got 3 levels of nesting going on here. And also within this outer loop, we have an if statement. And inside that if statement, we got another if statement. So you can see that you can nest various types of control statements within other types of control statements. And that gives you a lot of flexibility in the flow that logic can take, because that's what control statements are doing. Control statements are controlling the flow of execution. Without control statements, you'd have one statement execute, then another one, then another one, then another one. Everything would be sequential. But with these controls, you can repeat and you can make decisions. Do I want to go this way or do I want to go that way? And within every repetition, I could be making different decisions. Or within every repetition, I can have other repetitions going on as well. Here's another thing to keep in mind as we're making use of constants. And remember that the naming convention for constants is that they're all uppercase. So, if you have all uppercase and you've got multiple words in your variable, well, how are you going to be able to distinguish between the different words? Well, oftentimes an underscore is used to do that. You can't use a hyphen, by the way, because a hyphen is a minus sign. It's an operator. You can't use operators in your names, but you can use underscores. And the nice thing about using a constant here, I want to find 50 primes, right? And so if I didn't have this constant, I'd put a 50 here, and I'd put a 50 here. And then if I changed my mind and I said, no, I really want to have 100, then I'd have to change this 50 to 100 and that 50 to 100. So when you have a constant, you can just make a change to the constant itself and then use the constant multiple times. This can save you some coding. That's one of the advantages of using constants. Now they start with a number 2. 1 is kind of trivial to consider as a prime, so they're starting with a number 2. And as you can see, each time the number is increasing. And what is that number increasing? It's increasing every time we're in the loop. So we're always testing to see if the number is prime. The question is, how many prime numbers were there? And we want there to be 50. And that's why we're using this other variable count to keep track of every time we found a prime number, we're going to increment that count. So there's 2 different values that are of importance here. One is the number, which we're going to test to see if it's prime, and the other is the count, so that we will be keeping a count of how many prime numbers we encounter. The remainder operator comes in handy here. We know that if some divisor divides into a number, then it's not going to be a prime number. So notice this test right here. Look at this loop. For divisor equal to divisor less than or equal to number divided by 2, divisor plus plus, and why number divided by 2? Because we know that anything that's more than half isn't going to divide into the number. So every time we're testing to see, is this number divisible by that divisor? Divisor is our loop counter, so our loop counter variable is being used to divide into the number. Is it divisible, meaning it would give us a 0 as a remainder? If it is, we know that our number is not prime, So we're going to set our Boolean value to false here. And also notice that we were also using a modulo here. Number of primes per line was 10, so that's why we only wanted to see a maximum of 10 numbers on each line. And so this count mod number of primes per line is giving us a remainder. If it turns out to be 0, that means we've reached 10 for that one line, and that means we're going to want to go to the next line. And if it wasn't the case, all we want to do is print and keep our cursor on the same line. That's why you can see in this output, none of these lines have more than 10 numbers in them. And there's our divisor again. So here is another example, and we've seen examples of this before, where we're using our loop counter variable to do something, not just to iterate through. The loop control variable right here is also being used for something within the loop, to do a calculation. Here was our test to see if it was prime, so we made a Boolean, where notice in the loop here, in our outer loop, we're always assuming at first that it is prime. And only if we find a number in our little for loop here, if we find a divisor that will evenly divide into our number, do we decide that it's false. So if we never hit this line here, if this if statement never succeeded, then we know that that would have been a prime number at the end, and otherwise we know that it would not have been. And that's why we have this if statement here. If after we've checked to see whether it's prime or not, it is prime, then we're going to increment our count, and we're going to print. Notice also that how did we get out of this for loop? I mean, once we decided that it's not prime, there's really no need to continue anymore. Once we've decided it's not prime, might as well break out of the loop. And so that was what this break was for. So I encourage you to play around with the debugger here and see what's going on. In fact, I'll do a little bit of that myself. Maybe what I'll do is I'll put a breakpoint right here at the break statement, so that this is going to help us to identify any numbers that are not prime. And maybe also one right here I'll put it in this if statement right here. So that means that if it was prime, I'm going to increment my count. And let me just do this. I'll just run it, debug it for a few iterations here. You can see what's going on. Okay, for the first number, which was 2, obviously it was prime, so we have incremented our count. For the second number, which was 3, is also prime. But the third number, which was 4, is not prime. If we want to get what's number modulus divisor, it's giving us a 0. So therefore, is prime had been set to false. And then for 5 is prime, and 6 is not prime, and 7 is prime. And all the while, you can be looking at the variables. These are all local variables of the main method. Or I should say, args is actually a parameter passed. We'll talk about what args can be used for later on. But other than that, all of these are either local variables or local constants. And you can see what their data types are, and you can see what their values are. And as we iterate, you can see those values and data types changing. And note that every time something changes, it becomes bolded here, so you can see what has just recently changed since the last breakpoint. Debugger, very, very useful. So that's the discussion I want to do about from Chapter 5 right now. We will later readdress Chapter 5 stuff, because there is some material in Chapter 5 that has to do with the use of methods and other kinds of things that we haven't yet gotten to. The next lecture is going to be about arrays, and then we're going to start doing some text file I/O, And so that's what we have coming up. After reviewing that last lecture, I realized that I had made a mistake about something, and I want to point it out to you. I had said that count is telling you how many times we go through the loop. But count is not telling you how many times we go through the loop. Count is telling you how many primes we wind up finding, because we'll keep going as long as count is less the number of primes. We're not incrementing count every time in the loop. We're only incrementing count if it's prime. What we are incrementing every time in the loop is number. So number starts at 2, and we keep going and going and going and going until count is equal to number of primes. So it's going to take us a lot more than 50 times to find 50 primes. So I wanted to make sure that's clear to you. So as you can see from running it, we go all the way up to 229. So really we started at 2, and we kept going until we got to 229. Looks to me like really we looped 228 times here, not 50 times. So just wanted to make sure that that's clear. Another thing I'd like to point out is the scope of these variables. Notice that the variables that are being, and the constant, that are being declared in the main method have what is called method scope. That means every statement from here on down can access count and number. However, isPrime does not have method scope. It only has block scope. It only exists during the execution of an individual block and can only be accessed from within that block. I could not have another statement outside of that block that accesses isPrime. So it's a narrower scope and also a shorter duration, because number is going to exist throughout the entire time that main is active. But isPrime is going to exist, and then it's going to disappear, and then it's going to exist, and then it's going to disappear, and then it's going to exist, and then it's going to disappear. To illustrate that, I'm going to put 2 breakpoints here. I'm going to put a breakpoint at the while, and then I'm going to put a breakpoint inside the block of the while loop, right here after isPrime has been populated. And let's see what happens when we debug this. So here we can see these variables and constants do exist, but isPrime doesn't. So here we're about to enter the loop for the first time. And now isPrime exists. And now it doesn't anymore. And now it does again. And now it doesn't anymore. So this notion of the scope of variable, which means what instructions have access to it. And in this case, the only instructions that would have access to it, to isPrime, are the instructions that follow isPrime within the block of the while loop. And duration, how long does it last? And in this case, isPrime only lasts as long as a single block of the while loop is executing, and then as soon as we get back up to the top of the while loop, it's gone. Scope and duration kind of go hand in hand, and we'll be talking a lot about that as time goes on.